So here is not the model. It's just like the only math equation in the presentation, so don't start rushing for the door. This is not the model. Okay, the model, like I said, is very complicated. It's cool, but it's not important to the class. This is important to the class because this is the error function. This is when the model is training itself. This is the function that's looking at to understand whether it's performing well. So this isn't validation. Okay, validation is easy. We just test how well the points are matching. This is internally what's happening when the model tells itself that I'm doing a good job, I'm learning. And when it minimizes this function, it says this is the smallest error possible, and it gives you back that model for any set of parameters. And these are the parameters that are effective in this. And this is going to, the reason it's important is this is going to show us where the control is, where we can control the model. Okay? So in general, the function is just here, and there's an algorithm that tries to minimize this value. So the smaller the value is, the better the model is internally, right? As it's processing a lot of variations, it's trying to minimize this value. So there's the optimization function, which tries to minimize this. And there's two pieces, right? They're added. So this results in a number. And the bigger the number is, the worse the model. And there's two ways that the support vector machine decides whether it's a good model or not. One is based on parameters. W's are all the parameters that are assigned to each of your data points. It basically adds those up and squares them. Okay? What this means is the more support vectors it uses, the more of your data it uses, the higher this number gets. This part of the equation is the penalty for complex functions. So again, SVMs can get to any order of complexity, any dimensions, up to infinite dimensions. This is the part of the error function which will keep it from getting too complex. Okay? This is the part of the error function which penalizes the model based on errors. So these two are working against each other. On the one hand, it's trying to keep the model as simple as possible. On the other hand, it's trying to predict your training set as well as it can. Okay? Does that make sense? So we can go back to our linear model maybe quickly. So as we go from the red one to the blue one, right? We can think of the blue one as being a more complex model. Here the number is higher. In the case of SVM, it's other things. But there would be this trade-off somewhere where this model is performing better and better on the training set, right? That is this part of the equation. But it's using a more and more complex model. So you can think of the degree being here, like it gets higher, the error gets higher. But as it gets higher, the performance, the error is getting lower, right? So they're kind of balancing each other out. This is the minimization function. What's important about this is the parameters in this equation are the parameters that we use to specify the function. Because it's the parameters that it uses to say what is a good model, right? This we can't specify. This just has something to do with the way that it assigns weights. This C and E become our parameters. This is how we tell the function or the model what to look for. C is a general. So I'll give you these slides. You can read through this. C is a general multiplier. It says, in general, how important is error or performance. The bigger C is, the more it's going to focus on getting every one of those points right. Bigger C's create more complex models. Higher values of C will eventually lead to overfitting. This epsilon specifies the soft margin. It specifies the distance within which points don't matter in the error function. So the higher epsilon is, the bigger that soft margin is, the more points that are troublesome it's going to ignore. This creates simpler models, right? But it can create underfitting. So you might make the model so simple that it ignores actual structure in your data set. And when I use this overfitting high variance, underfitting high bias, these words, variance bias, this is something you'll encounter a lot in machine learning literature. It's not super important to us. It's just enough to understand how C and E works, because we're going to use those to train our models. But basically, it's good to understand the difference between variance and bias. I have this diagram here. This is how a lot of machine learning people talk about whether their model is overfitting or underfitting. And it's two types of errors that can creep up in a model. Okay, so say in this case you have this point where it's the perfect right model, right? You don't know this again, it's just based on some validation. But there's some potential model out there that's the right model. It's not gonna be error-proof, right? Because there's always noise, but it's the right model for the system. As you gain complexity in the model, as you get more and more complex, we have the problem of high variance. And that is that our model, although it's very complex, it can vary wildly. So if this blue point based on error moves just a little bit, the whole model will change a lot. And that's why it's called high variance. The model is so complex that any noise in the data will vary the model drastically, and it usually results in overfitting and bad generalization. So in this case, the dashed dot is our right model, and this is the case of high variance overfitting. The 11th degree model suffered from high variance. And there's another source of error in the model, which is the opposite. It's high bias. And this is called underfitting. It's where the model is too simple. It's so simple that it doesn't capture the actual structure in the data set. Okay, so if we decrease the model complexity and get as simple as possible, once we cross this point, it will actually underperform, not because it's high varying, but because it's very biased. Okay? This is the idea of high bias. And you'll see this bias versus variance trade-off as a huge part of the literature. If you go to those Caltech courses, he devotes a couple lectures to the bias-variance trade-off.